monthly webinar series. We're fortunate to have an array of outstanding speakers presenting the results of their research during these webinar series. And I won't take much of your time. The technical committee focuses on sharing different aspects of induced seismicity research with the ARMA community and policymakers. And we also try to develop focus group discussions and workshops. And along those lines, I would like to remind you that there will be a workshop during the annual ARMA Rock Mechanics Symposium, which will be held in Santa Fe, New Mexico, from June 26th through the 29th. So the Sunday before the conference, we will have a workshop on induced seismicity. The details of this workshop will be shared with you ahead of time so that there will be sufficient time to consider submitting an abstract and participating in the workshop and sharing your thoughts. I'm the chair of the committee. Sean Maxwell is our co-chair, and he has been leading this effort for the past few years, along with Jens and Mahdi, who mostly organized the webinar and are doing a fantastic job inviting people and arranging for different presentations and publicizing the results. And for those of you who are not familiar with ARMA, I'd just like to mention that this is essentially an organization that enfranchises different groups who are interested in subsurface science and engineering, from mining to petroleum to geothermal, and geoscientists as well. And it's unique in this aspect. It integrates different disciplines, and we would like to invite everybody to consider joining this organization and attending the conferences. So that is all I have to say, and I can invite maybe Sean if he wants to say something, introduce our speaker.
Absolutely. Thanks, Ahmad. Good morning, everyone. So continuing on with our webinar series, today we're very excited to have Serge Shapiro, Professor of Geophysics at the Free University of Berlin. So I've known Serge for a number of decades. I think back in the early days of microseismic, we were maybe one of the few people when it was considered a niche technology, so the times they sure have changed, Serge. But Serge has had always a very interesting view of microseismic, including seismogenic index concepts, which is something that's over the last several years become more commonplace in terms of forecasting induced seismicity. So Serge has really kind of pioneered that work. So today we're very excited to have Serge talk about his work and get it directly from the source, the concept of seismogenic index. So with that, I'll pass it over to, we can maybe move ahead to the schedule, and we'll pass it to Jens to talk about the schedule.
All right, good morning, everybody. I'll just announce two upcoming speakers. We have at least two more who are exciting speakers likely to be announced soon. In early January, Jim Dietrich from UC Riverside, formerly USGS, will be speaking. That date, 10th of January, is a somewhat tentative one. We're trying to avoid at least the first part of that month because of the holiday. So stay tuned on that date. It may be on the 10th of January. And then the following month, we'll have Cody Comiskey of Chevron speaking about work by the Texas Oil and Gas Association Seismicity Working Group. That'll be the first Friday of that month, the 4th of February. Thanks.
Good morning, everyone. This is Mahdi Haddad at the Bureau of Economic Geology. First of all, thank you so much for joining us this morning for another great webinar by Serge Shapiro. This is a community of geologists, geoscientists, and petroleum engineers, and we have almost 500 people in this community, shared between academia, regulatory agencies, and the industry. We encourage everyone to send the invitation email to the colleagues who are interested in induced seismicity to increase the size of this community, to share the technical content to everyone over the globe. For this webinar series, we have some simple rules for better flow of the webinar. First of all, everyone will be muted during the talk, and you can be unmuted at the end of the webinar for asking questions personally. And please submit your questions during or after the talk in the chat button at the bottom of the Zoom meeting window. And please send these questions to everyone for summarizing the repetitive questions and using the time better. And this specific Zoom meeting is recorded and will be uploaded in our YouTube channel. Please subscribe to our channel in order to be updated about the upload. And without further delay, let's invite Serge to share the screen and take the stage. Serge, thank you.
Okay, yeah, thank you very much. But so my screen is already there. Can you see my screen?
Not yet.
This is surprising. So now, okay, what about now?
Yes, it's good. Yeah, thank you.
Very good, excellent. Okay, hello everybody, and thank you for inviting me for this presentation. This is a very interesting community where I'm very seldom giving my talks. Hopefully it will be interesting for you. So let us go ahead. So I will speak about applications of the seismogenic index concept for forecasting induced seismicity. And I will start. So this is exactly what, I will start with a short introduction of the concept of the seismogenic index. The first what one must introduce here, and I think that this what you know very well, is the Gutenberg-Richter statistics for description of magnitude of or magnitude statistic of earthquakes. These are two examples of fitting of the Gutenberg-Richter equation, which describes the number of earthquakes with magnitudes higher than this given magnitude m. And this is just a straight line, which is parameterized by two constants, constant A and constant B. These are just constants of the Gutenberg-Richter statistics, just of this equation. So basically this is a straight line, and on this plot, where on the horizontal axis you have magnitudes, and on vertical axis you have number of earthquakes with magnitude higher than given one, given this m. And these are two real absorbed seismicities from the Pohang enhanced geothermal system. Pohang is in South Korea. This is a city in South Korea, and people attempted there to stimulate a geothermal reservoir from two boreholes, one borehole and a second one. And by corresponding injections, they produce seismicity, earthquakes. And for example, this is the second borehole. And you see here, this is the number of earthquakes with magnitude higher than given one, and higher than shown here. And this is just the Gutenberg-Richter straight line fitting of this of this statistics. So usually this statistics works quite well, starting the so-called completeness magnitude. So this approximately this one, and before completeness magnitude. So this approximately here something like minus 0.5, or maybe something like close to 0. Below this magnitude, earthquakes are not recorded completely, but above this magnitude, people interpret this such slides usually like such figures usually like, now starting this magnitude, say we have a complete registration, and then statistics is very well given by this straight line. So this is the Gutenberg-Richter statistics. You see here is also
Serge, I think you accidentally muted yourself. Can you unmute?
Yes, somehow. Yeah, so
yeah, that's good.
How long time ago I have muted myself?
Just a few seconds.
Just a few seconds. Okay. Okay. So now, so this is again, this is a Pohang case study where people try to stimulate a geothermal reservoir. So and they produced seismicity by injections of water in 2 boreholes. And you see here, this is what they observed in the first borehole. This is what they observed in the by injection in the second borehole. These are earthquakes. You see here their magnitudes. So these are magnitudes. There's a scale of the local magnitude that's quite close to the moment magnitude. And so they produced earthquakes of the magnitude 1, 2, 3, so in this range. But at one moment they produced magnitude 5.5, and this was already a huge, of course, a huge, terrible event, a huge problem really for, this was a damaging earthquake. The geothermal system was quite close to the Pohang city, and there was a damages in the center of the city, and even some injured people. So this was not a good event. Now, I'm not sure, can you see the title of the slide? Because on my screen, it is covered completely by this menu.
Yeah, we can see it, Serge.
You can see, okay, very good. Now, this Gutenberg-Richter in this standard form, what I show here in the first equation here, it is a standard equation which is applied for tectonic earthquakes. And again, these are 2 parameters, A and B, what people usually see in tectonic seismicity. And parameter B is usually quite close to 1. And parameter A is, of course, a function of time, because the longer we observe seismicity in a given region, the more earthquake will be. And so this is why A just increasing with time. Now, basically, if we assume the same statistics for statistics of magnitude distribution for fluid-induced seismicity, then one can precise this parameter A. And this parameter A then has the following form. So this is what we have instead of parameter A for fluid-induced seismicity. So, and the conditions here are the following. You go, for example, to your borehole and can start to inject fluid, and you do this monotonically with non-decreasing injection, and you will see that the more you inject, the larger volume of fluid you inject, the more seismicity you will get. And basically, under assumption that all seismicity what you produce is triggered by pore pressure perturbations. The second assumption is that the probability of producing an earthquake is proportional to the pore pressure perturbation. Then just by integration over the space about an integration of all pore pressure perturbations in the space, one will obtain just this expression for this parameter A. The parameter B will stay the same, so just characterizes the seismotectonic features of the region. And M is the magnitude, so all other things are here exactly like in the Gutenberg-Richter equation. But now we understand better this parameter A, and it is of course a function of time. This is the decimal logarithm of the cumulative injected volume of the fluid, which assumed to be approximately incompressible. But basically, there should be a mass here, but then you need additional coefficients. But volume is a convenient thing. So this is a good approximation for this in the case of these two assumptions. And firstly, this was proposed this model was proposed in 2010 and published in the Leading Edge, and Sean was even editor-in-chief of this special issue of the Leading Edge, where we published this firstly. And then it was developed in a series of other papers, and even it goes, and I will show you even very recent things from this year, just from a couple of weeks ago. So this model of seismogenic index, so if you look again at this model, so this sigma, what is put it here, we call it, this is a constant. And I will show you explicitly how this constant depends on characteristics of the medium a little bit later. But basically, this sigma characterizes also the seismotectonic situation in the region. So sigma and B, these are two characteristics of the seismotectonic situation of the injection site. And basically, if it is a constant, then the n, the number of events with magnitude larger than this given one, behave as function of time exactly like the cumulative injected volume. So this is what this model states. So this is an observation in Basel enhanced geothermal system. This is also a famous example of producing earthquakes, significant earthquakes by fluid injections for stimulation of geothermal systems. And what we see here, the blue line, this is the injected volume. So basically a normalized injected volume. Basically, this is blue line is nothing else as the seismogenic index model. And the red line, this is exactly induced earthquakes, number of induced earthquakes, also normalized here just to put these two curves close to each other. This is cumulative number for of earthquakes with magnitude higher than 0.5. This was the completeness magnitude there approximately. And you see how nicely they are following each other. So these two curves. So this means that the seismogenic index model, at least in Basel, works nearly perfectly. At this moment of time, this is the times axis, and so these are this axis of these two normalized constants. Now, and there's this normalized quantities. Now, at this moment of time, an earthquake, a significant earthquake, magnitude 3.2, something like this, happened, and they stopped the injection, and moreover, they opened the borehole, and there was a flow back and flow out of the fluid, and you see that the volume of the fluid, the cumulative volume of the fluid decreases now, but seismicity, of course, continues to increase. And now there is a discrepancy, of course, between the seismogenic index model in this very simple form, what I have shown you before, because there is no anymore the injection is not anymore monotonic. And of course, in this domain, one can also apply this model, and I even will show you later an equation what to do there in such situations. But one needs then more numerical computations then. So not such a simple form like before. Okay, now if we have so this is, yeah, okay. Now, if we have, I hope very strongly that you can see this equation. Because I don't see this again, so because it is covered in my on my slides by this.
Yeah, we can see it, Serge.
Very good. Now, if you have, thank you, Sean. Now, if you have your induced seismicity, and if you know your magnitude, what you register, and this is usually the case, and if you know an estimate of the B value, which is usually quite close to 1, then you can compute seismogenic index. You can even do this for seismogenic index as function of time. And we did this for various locations, and these are just seismogenic index as function of time computed for various locations. Yeah, so this, for example, these magenta lines, these are famous Cotton Valley hydraulic fracturing experiments, several hydraulic fracturing experiments there. Yeah, and then the green one, this is one of famous publications on Barnett Shale. Now, these blue lines here, these are KTB, this is a continental deep drilling projects in Germany. So the red lines, these are Sulz. So this black line, this is Basel. And one usually see that the seismogenic index is quite constant with time. This is just a normalized injection time. So here there are injections which are a couple of hours long, or a couple of days long, on even 10 years long. So there is here paradox value, for example, a couple of something like 10 years long injection. Well, the seismogenic index is nearly constant, and it must be so because it's a characteristic of seismotectonic situation in the medium. This is just a quantification of seismotectonic conditions there. Yeah, so a kind of characteristic quantification of tectonics. So, for example, the blue one here, the blue domain here, this is an estimate for Groningen gas field. This is not anymore injection, this is fluid production. It's very interesting, and I also will comment on how we got this one. And this domain, the red one, so this, the rosa one, this what we got for Pohang. So, and basically, so the largest what we have ever observed, this was for Basel. But for Pohang is also not a small one. So the highest seismogenic index, the highest the probability of having significant earthquakes. Now, by hazard of induced seismicity, maybe the most important role is considered by a maximum expected event, or maximum event what you can produce by your stimulation operations. And this was recognized already a long time ago, and there are already attempts to use the seismogenic index for predicting the maximum expected magnitude of stimulated earthquake. This is an example of such prediction. So this is a slide, a figure what I took from the paper of Galles, and what we observe here. These are all points here. These are maximum observed earthquakes in various locations around the world. You see here very different sources of very different types of experiments: hydraulic fracturing, scientific fracturing in geothermal, injection for geothermal systems, disposals of fluids, hydraulic fracturing again, and so on, and even laboratory experiments, and even in situ experiments very close to the surface, so in tunnels type of or in mining type of environment. So basically, the horizontal line here, this is the injected volume, and the vertical line here, this is seismic moment or magnitude. So this is maybe convenient scale. You see here the moment magnitude, and this is the 6. This is the largest one, maybe, and basically, what one can see here. This is the famous McGarr estimate, which provide so-called upper cap, the cap of maximum possible magnitude. But you see that there are already observations which significantly, which are higher than prediction of the McGarr equation. And these are the McGarr equation is just saying that the seismic moment of maximum expected magnitude is proportional to the injected cumulative injected fluid volume. And there are a similar model, but computed from different consideration as by Galles with co-authors. These are these three lines, and they are already calibrated here with the seismogenic index. You see here, seismogenic index 0.7. This is maybe the largest, even larger than in Basel. Yeah, and this is also significantly large one, and this is significantly high one, and there's also a high one. So these are three lines calibrated by the seismogenic index. Yeah, here. But they have a different inclination. Yeah, they show that the seismic moment is proportional not to the volume, but to the volume power 3 second. And this model of Galles with co-authors, it coincides with the model with the estimate of maximum expected magnitude by van der Elst, which directly uses the seismogenic index. So basically, it says that if you have Gutenberg-Richter statistics of your earthquakes, then the maximum event corresponds to the number of event equal 1. Yeah, so it's just the number of event then is just equal to 1. And then if you substitute this there, then you can estimate maximum magnitude just from this equation. This is a very nice equation, directly using the seismogenic index, and these are exactly these calibration lines. And so because these two models, they coincide with each other for B value equal 1. And this is usually the case. So the B value is quite close to 1. These all three predictions are not bad. They describe situations not bad, but there are some problems here, because already the McGarr one firstly doesn't describe really the tendency here, and also doesn't describe this already earthquakes. But even more, the point was that the Pohang one was already higher, significantly higher than all of them. Yeah, so they cannot predict the Pohang one. So this means that these two are just, this model of Magar is contradicting these two. And then, and these two models, they do not describe very large earthquakes. And what is the problem here? The problem is that if you have just the Gutenberg-Richter statistic and assume that you have just one single event as the maximum one and expect that your maximum correspond to exactly this n equal 1, then you can even estimate the probability of such an event. And then you will see that, that this equation describes an event which has probability 63%. Or 63%, this is an extremely high probability. Such event will occur for sure. Yeah? And it's clear that it cannot pretend such an estimate to describe events which possibly can occur, but whose probability could be maybe 20% or maybe 10%. What about such events? This estimate doesn't provide these magnitudes. So why actually these equations not really successful for extremely large events? So we have recently published a paper where we tried to, so this was paper targeted to Pahang earthquake. And this is exactly the figure, what I have shown you before from the Gales paper. So the paper, this is a publication, what I speak now about. And but this figure just is for slightly just replotted here. These are more or less the same events. But now we have here the Pahang one. So this is again the scale of the injected volume, and this is the seismic moment or moment magnitude of the maximum event, of the maximum observed event. So these are various possible earthquakes in various locations around the world. Now, what we did, we took just not the logarithm of the cumulative injected volume, but just decided to look what will happen if we plot the maximum observed earthquakes for all these case studies, but not as a function of the cumulative volume, but as a function of the nucleation time of the earthquake. And this is this plot. These are exactly the same earthquakes. So this is a line which would correspond to the Magar estimate. And this line which would correspond to this estimate. Where I'm getting these corresponding equations, I'm just looking here for analogous volumetric dependencies, but actually the most important here is the dependency on the nucleation time. What means here nucleation time? This is the time for occurrence of this earthquake, but counted from the start of fluid operations at the given location. So these are exactly the same plots, but without any lines. And on these plots, we concentrate only on this part of earthquakes and this part of earthquakes. And they are why these parts? These two clouds, these two small clouds are disregarded because this big one, this big set of earthquakes was observed from by injections in deep boreholes. And this one is laboratory, and this one is mining on tunnel type of injections very close to the free surface. So the boundary conditions, of course, for such observations are different than if you consider if you make injection in deep borehole. Here you work nearly with the infinite medium, and here you have very close free surfaces. So this is why it is interesting to concentrate on a kind of pure and nearly infinite medium approximation. So if we consider these two sets of plots, we will see immediately that on this plot, the Pohang earthquake is excellently belong to this set of points. Then this set of points seems to be more compact, and interesting is that if I would put here such a straight line, sorry, this must be straight line. So this would correspond to this one. This would correspond exactly to a type of pore pressure diffusion process in the medium. If we assume, so basically it comes from consideration that the moment magnitude of maximum earthquake, what we can trigger is depends on the scale of volume what we stimulate, but it doesn't mean this maximum earthquake must sit inside of this volume. It can be also such a geometry. You stimulate such a volume, and your earthquake sits something like this. Just the probability of intersect a large fault depends, of course, on the size of the volume what we stimulate, and this so this increase with time of this volume during the injection and corresponding and this line, they are very well described by power law of time corresponding to a diffusion process, just a normal diffusion process. So the pore pressure diffusion seems to be responsible for triggering of this maximum observed events. So now what we did then at the next step, we attempted to propose then an approach how to predict or what can we do to make a kind of prediction of maximum earthquake what can occur by fluid injections. And we used now not just volume, and we cannot also use the nucleation time, because nobody knows the nucleation time. The question is then what to do. So, and of course we took as an example this Pohang earthquake. So this is the Pohang EGS, and this is earthquake. What happened there? And the city must be somewhere quite. I think that this was to the north from the city and quite close to the city, so something, so just very close to the city. The people drilled their two boreholes. You see here, this was this PX1 and PX2, and the earthquake happened already somewhere here. This was this 5.5 hypocenter was somewhere here, but I will show this in more details. So this is, by the way, South Korea, Seoul, and this is the Pohang. Okay, so what we propose to characterize the largest, so the maximum magnitude earthquake. We do not predict the size of the earthquake. What we propose is to do the following. we propose to observe, to monitor a worst case probability of a given earthquake. If we assume that an earthquake of magnitude 5 or 5.5 is damaging and we don't want such earthquake to occur, then we propose to observe probability of, with the worst case probability of such an earthquake. Now, just to see what will happen if we do this for Pohang, we produced the following computations. How to compute this worst case probability? So basically, if we assume the induced seismicity as a Poissonian process, then probability of earthquake with magnitude higher than m, so this so-called exceedance probability, is given just by this equation. Then this is the n. Here is a number of earthquake with magnitude higher than this m. And of course, here it is assumed that just the Gutenberg-Richter statistic, just the standard Gutenberg-Richter statistic. Now, if we can combine this equation just with a seismogenic index model. So we substituted here, instead of this n, the seismogenic index model. And this is exactly the seismogenic index model. But because we speak here about the worst case probability, we take each time we estimate the seismogenic index. So basically, seismogenic index should be constant, as we spoke, as I have shown before. And also, what one should also, of course, and what we take here, this, of course, the upper bound of the or supremum, as I put it here, of observed seismogenic index as function of time. So why I put it this as function of time? Because let's assume that you produce your stimulated volume is increasing, and at one moment it starts to touch more seismically active domain. Then it is possible that seismogenic index will increase. And frankly saying, we have seen such an increase in Pohang. Now, for having here a really worst case, I also put it here infimum. So this is the lower bound, the estimate, the lower estimate of the b value as function of time. But this one we never did. We just took the b value from as a constant from tectonic publication about seismic tectonic features of this region. So, so this means that this was constant, and this we really attempted to estimate for stimulations at the Pohang geothermal system. Yeah, so this means that clear that if it is maximum and this is a minimum, or this supremum and this is infimum, then this provide a kind of worst case approximation. And this is the injected volume, the cumulative injected volume. So what we propose that that one should choose a dangerous magnitude m, what we don't want to occur, and then observe this probability as function of time during the injection experiment. Now this this m for the Pohang case study, we took just exactly equal to 5.5. And this is what happened at Pohang. There was a mud loss, firstly, by drilling of the second borehole. And then there was injection in the second borehole, and this blue points here, blue circles, this is magnitudes of induced earthquakes. And you see here all of them. The magenta line, this is the cumulative injected volume the green one, this is the bleed off. And so we use this data to compute the seismogenic index.
Hey, Serge, sorry to interrupt, just a quick time check, maybe 10 minutes so we can have a few minutes before the close of the
10 more minutes, okay.
Yeah.
Okay,
Thanks.
okay. So what we see here, this is the behavior of the seismogenic index as function of time. This is approximately its upper bound. These are earthquakes observed, induced earthquake observed there above the completeness, approximately above the completeness magnitude. This is the magnitude 5.5. And this is how this equation of van der Elst predict the maximum magnitude. You see that already this equation has problems with this one. And then what we did, this is again Pohang earthquake. This is the stimulated earthquakes. This is the Pohang big earthquake, and this is its rupture domain. And what we did, we attempted to estimate the probability of such, as you can see this, a kind of a runaway event or runaway rupture. This is the stimulated volume. This is the runaway rupture scheme, yeah. And we also estimated a probability of an event of the size of the stimulated volume. So this event, this is a Pohang one of magnitude 5.5, and this is of magnitude between 4 and 4.5. And this is the worst case probability. This is the red line. And you see how it behaves. There was an earthquake with magnitude 2.3. There was a kind of significant jump of the probability, this probability in percent. And there was an earthquake of magnitude 3.3, and there was a jump of probability to the 15%. This already significant probability. What about this one? This is a probability of such stimulated volume size event. And after the magnitude, this is the magnitude scale. After the magnitude 2.3, its probability jumped to 25%, a very significant probability. And already after the 3.3, it's jumped to nearly 80%. And so if I have a high probability of such event, there is a guarantee that it will not grow up to this size. So this means that already this situation is very dangerous. I'm not speaking already this one. So this is why it is clear that one should actually keep seismicity so by this level, yeah, so approximately by this level. So this is approximately magnitude 2 and below. So this is just an intermediate conclusion for the Pohang part of the talk. So maximum magnitude earthquake scales with log nucleation time, and such earthquakes are likely triggered by the pore pressure diffusion. The seismogenic index of the Pohang site was approximately between -2 and -1. And during the stimulation period, sigma increases, an indication. This was an indication of a gradual stimulation of seismically more active zones, and the event of 3.3 indicated a jump of sigma to -1. The worst case probability of Pohang earthquake was about 15%. This is quite significant one. And there's a low B value. This B value was there about something like 0.7, and a rather high seismogenic index of this level, so up to -1, made this probability very high. And at the Pohang EGS, induced events of magnitude higher than 2.0 should be considered as a critical. So very recently, this is a very recent work. So actually the first one was 2018, but the last one was just a week ago. We further generalized the seismogenic index model. So again, this is the standard Gutenberg Richter. This is the seismogenic index for fluid injections. And this is now a seismogenic index model for arbitrary processes which are impacting the failure Coulomb stress. The seismogenic index, actually the tectonic one, is defined here by sigma 0, and it is a function of concentration of cracks in the medium where earthquake can happen, and some other parameters. And what is put it here, this is an integral of the Coulomb failure stress perturbation in the medium. Actually, it must be a monotonic positive upper maximum, a monotonic positive minimum measurand of these things as function of time. And this is the uniaxial storage coefficient, and this is the friction angle. So if this one is computed, substituted here, one can use the seismogenic index model in very general situations, and for not only monotonic injections, but arbitrary things. So for example, one can use this for production, and we use this for production. It's approximately such an equation for productions. So approximately, this is a very rough approximation, and basically I just will not, now I will skip a couple of slides and just show you how it works. So this is in Groningen. You see here production, and you see here the number of earthquake with magnitude higher than a given one. And this in this period of time, and later this is this period of time again. This is the theoretical line of seismogenic index model, and this is observation number of events induced by production, and this is the produced gas volume. So the gas field in Groningen in Holland. This attempts to estimate the seismogenic index. So look, so this is there. Our estimate was for seismogenic index between -0.5 to -4. So look, what is interesting here, if we make a plot for the total period of production, so this is 2016, and they started at 93, then you see here the production volume. This is number of events. These straight lines, these are lines for seismogenic index models with constant seismogenic index. And this red line, these observations, the observations show us that seismogenic index increased there with time. It increasing with time there. This is very interesting. At Groningen gas field, seismogenic index increasing with time from -5.5 up to maybe -4.5 or something like this. This is not a big one, but this increasing tendency is not good. And why it happened? There is an interesting. So we proposed a hypothesis published recently in rock mechanics and rock engineering that by producing gas, you continuously increase your differential stress in the reservoir, and you continuously increase your more Coulomb circles from this black one to the dashed line, and you're starting to touch faults which have higher cohesions, yeah, and if you and cohesions they impact the stress drop of produced earthquakes, and correspondingly then impact the seismogenic index. And seismogenic index, actually, it is correlated with the average stress drop of induced earthquakes. And so the more cohesive faults we are bringing to instability, the higher will be the seismogenic index. Then actually by monitoring the seismogenic index as function of time can provide information about the evolution of your seismotectonic state of the reservoir. So growing seismogenic index can result in an increasing maximum magnitude. So this can happen also in Groningen. So if you have increasing seismogenic index with time, then your maximum magnitude can increase. And what I have also shown you at one of slides is that we have recently generalized the seismogenic index to arbitrary physical processes impacting Coulomb stress. So thank you very much, and I'm ready to respond your questions.
Great, thank you, Serge. A lot of really interesting, intriguing observations, and can read off maybe a few questions. And if you're available, Serge, what we often do with this is continue more of an informal Q&A.
Oh, yeah, I'm here. So
okay.
I'm here. So let us go ahead.
Okay. So one question, an interesting one from Zian Li. He was wondering about the sign of the seismogenic index. Most are negative, but he was wondering if they could be positive. But I'll maybe generalize it. Do you think there's an upper bound on a seismogenic index?
If I go to the equation for the of the seismogenic index model, so this one. So basically, seismogenic index can be negative and positive. And if you see this in this equation, it has also a very strange unit. So basically, this combination has no units. So this is, and seismogenic index has units of minus logarithm of volume. So this is why to work with seismogenic index, one must agree about the units in which you compute your injected volume. And what we did, what you have seen on this slide, this all are for the system international. If you assume that, if you accept that your volume is measured in meter cube. So basically what we have observed is between -10, so these are sedimentary rocks usually, and above -4, these are crystallines. So geothermal stimulations people usually doing in crystallines, because these are more hot rocks, yeah, usually, yeah, so tectonically. And the largest one what we have seen, this was in Basel, so something like plus 0.4. So I don't know if there is an upper limit. This is a good question. This is a question of tectonics, yeah. So, but I assume that because there is an upper limit of largest possible earthquake on the Earth, yeah. So you cannot observe earthquake of magnitude 10 or something like this, yeah. Then there is of course an upper limit also on seismogenic index.
Excellent. So there's some other really good questions on the Q&A, but I'll maybe kind of just wrap it up with a question of my own, if I could. It ties into what you were just saying, the distinction between softer rocks, more crystalline, brittle rocks, and the difference in seismogenic index. But Serge, do you think there's a way we could kind of pre-characterize, just thinking about things like CCS, where we're looking to go to a site and we want to risk the chance of seismicity?
Yeah.
Is there a way, do you think, we could characterize beforehand the seismogenic index?
Yes. So of course, the best way is to go at a given site and make small injection experiment, but big enough for producing seismicity a little bit, and then to compute seismogenic index, and then use it further for your experiments, for your planned experiments. But if it is not possible and before any experiments, so there is a paper by, so I apologize, so just a second. There is this paper where we attempted to correlate seismogenic index with the observed peak ground acceleration. And there is some loose correlation. There is also some loose correlation between seismogenic index and the depth. And one can use these correlations to approximate these correlations and also this, this plot to approximately tell that I expect seismogenic index for a given, from a given region, from a given range. Yeah, so if I go to sediments, I would not expect seismogenic index there. I would say if I work with sediments, I would maybe use this range as for very conservative estimates, something like this.
Thank you.
Or again, use this paper, look at these correlations.
All right, well, we've reached the end of the hour, so so I'd just like to thank you for the presentation, the excellent overview of the material, and it's a virtual meeting, but I'm sure I can speak for all participants when I say we all appreciate your efforts and the summary of all this great work. And just a reminder to everyone, the next webinar will be early January. The exact date still being pinned down, but Jim Dietrich will be talking about rate state frictional models.
Yeah. So there is. I have seen there are questions in chat.
Yeah. So let's. I just wanted to let people kind of formally wrap it up, Serge, and maybe what we'll do is just invite the other chat questions to unmute themselves. And I see Ryan there. Ryan, do you want to unmute yourself and ask your question?
Yeah, I'm happy to if we're done with the formal part. So I had a question. It sort of got partly answered because I asked it halfway through because I just saw that you did a generalization of the seismogenic index model for other types of seismicity. So if you have just like poroelastic effects or anything that affects that Coulomb failure function. But I am curious for what are your thoughts on how you handle scenarios like Pohang, for example, where they actually do flowback midway or after stages of stimulation, where it's maybe not clear that you can directly measure what that difference in the flowback seismicity might be, or should it just be expected that you're going to have reduced rates of seismicity from that? Because I guess part of why I'm asking this is because it's going to be on top of kind of like an aftershock-like decay where maybe you can't actually measure directly just the seismicity that's happening from flowback.
Okay, so let us look at the Pohang. How can I remove? Okay, so. Okay, so this you see this is the green one. This is the volume of the bleed off flowback fluid. Yeah, so basically it was not a lot. So they injected and then there was a flowback quite insignificant. But we took this into account by computing this. So this one was computed by accounting for the flowback. So we extracted flowback from the injected one, and but basically, of course, so the best would be here to make a precise numerical modeling of what is going on. But the point is here why I have not did this. We have not done this because to make a numerical modeling, you need already a very precise, rather precise idea about how your medium looks like. And of course, I could do this modeling for assumption of a homogeneous medium. But my first idea was that let us do this in very rough approximation. And so we estimated seismogenic index here in two ways. In one way, we just considered each of these injection stages as independent one and computed seismogenic index for each of these stages. And of course, accounted only for events which occurred during the injection, maybe a little bit, also include maybe a couple of events immediately after the stop of the injection, but basically we attempted to concentrate only on the injection time. And another estimate was done if you consider all this like a continuous monotonic experiment, what is of course a very, very rough approximation, very rough one. But they both surprisingly gave not such extreme different seismogenic indices. So this was a good range, so say a good bounce for them. So this is what we did. So because the magnitude of all these events is not extremely high, the aftershocks are not important. And anyway, maybe the aftershocks were only after this one with magnitude 3. I mean this sequence of events. But basically, we have not took them into account. We anyway stopped all estimates approximately here. So this, of course, you should not work with aftershocks, and ideally you should not work with aftershocks. And I am usually by fluid injections in boreholes. You don't have a lot of aftershocks because your induced seismicity is not large, not high, not strong magnitudes. Yeah, so this is. But basically, you are right. So one should also think about aftershocks.
Good point, Serge. The best way to mitigate aftershocks is mitigate the foreshock. Thanks, Ryan. So Paul Weir has a good question. Paul, are you still there? Do you want to?
I am. Yeah, thank you very much for a very interesting presentation. Appreciate that. So you showed how the seismogenic index adapts once you enter a higher, a more responsive zone. But my question is, once you enter that zone and you have activity happening that's both in a higher index and a lower index, are you then naturally going to underrepresent the higher index zone because your index is trying to accommodate both of those?
So I'm not sure that I completely understood your question. So basically, if you inject and you work in a stationary homogeneous medium without with a given seismotectonic characteristics, then seismogenic index should stay constant.
Right.
As soon as you and if you So this should stay constant because this is so. What maybe let me show you.
Yeah. So the question is perhaps when you enter a Pohang type situation.
Yeah.
Where your injection is now influencing another zone.
Yeah.
That responds differently. The first zone is still active, but you now have another zone that has a index.
I see.
And so you're trying to accommodate both with what number? And the question
is so of course, I understood you. So I think that in this case, seismogenic index represents just an integrated zone. So the first one and the second one together. Yeah. So you just you have so maybe if this means that can you see my screen?
Yeah.
Let's assume that this is your stimulation volume. Let's assume that there are two halves. This is the upper one is less seismically active. The lower one is more seismically active. You start injection here, and then you firstly obtain seismogenic index, which is low. Yeah, and then with time, your stimulated volume is increasing. It starts to get larger. This is the idea. Yeah, maybe if I would start the injection from here, I would firstly see very high seismogenic index, and then if it would go up, then I would see then the lower and the lower one. So by the way, the seismogenic index tectonic one is given by this is the logarithm of probability of earthquake with magnitude higher than 0. This is the concentration of defects in the medium, so where you can produce earthquakes. This is the uniaxial storage coefficient. And this is the critical pore pressure, or if you want, critical column stress divided by the friction by this sinus of friction angle. What you need to perturb all these cracks in the medium. So this is the Tectonics Esmogenic index. So this means that if it is homogeneously distributed in the medium, you will have this constant. If it is evolving, so for example, you have here a borehole and you have here an active fault zone. So if you go from your borehole to here with your stimulated volume, you will slowly, and maybe not slowly and quickly, increase your seismogenic index. Yeah, you will have a kind of jump. And this is what was observed in the Pohang. Yeah, seems to be.
Yeah, so it seems that in that case, there's a possibility that you would increase your probability of a larger magnitude earthquake,
yes,
but you may not increase it enough.
Yes, yes, okay. Yes, and this is correct, and this is a correct statement, and so this is actually the reason why we considered the probability of such event. So because basically, of course, the all information about seismogenic index what we have is from the stimulated volume. It is not from this zone. Yeah, this zone is outside of our vision, so it is invisible to us. Yeah, and so this is why this probability was extremely indicative. Yeah, so look, it is already 80% that you will get such an event. Yeah, but if your system is unstable, then this one can grow then further. Yeah? So then so this is why. Strictly speaking, I can speak only about events of this size. So we also attempted, of course, to estimate probability of this one, and this was such one. But in reality, maybe it was even higher.
Thanks.
Okay. So should we go to chat? There are there.
Can I just jump in quickly because it's related to the same issue. Very interesting. So even if you assume a homogeneous rock, right, and you inject into it, and there are no faults nearby, the seismogenic index of that system should also change with time.
Why?
Because the rock goes into a critical state. So you start propagating microcracks, and you get localization taking place. So even in that, there should be some kind of a change eventually. And related to that now, how about the time variance of B?
Yeah,
so
okay.
2 questions.
So there are then 2 questions.
Yes.
So the first one, that we make injection and we change the medium. So yes, we change the medium definitely. So so if we go to this equation, then by making injection, we can change here a couple of parameters. Yeah. So, but I assume that this change is not extremely high. At least look at this these observations. So this is Basel. This is the start of injection. They even decrease their seismogenic index. So this is this one of these guys is Paradox Valley, 6 to 9. So this is Paradox Valley. Paradox Valley is 10 or 15 years of injection. The seismogenic index is constant. So there are some situations where you see some increase of the seismogenic index. This KTB. This German experiment. This was not a monotonic injection, so one should look there more precisely into numerical stimulation. So you definitely change medium by your injection, but not. But this is a kind of nonlinearity, and this nonlinearity can be, in first approximation, I assume, neglected. This is to the first question. The second question was about the B value. And B value, this is also a great stuff. From my point of view, B-value characterizes the statistics of length distribution of your defects, the size distribution of your faults. And definitely you can go from one region to another region by your stimulated volume, where you have different statistics and different B-value. But the point is that to observe B-value evolution this time, you need extremely good seismicity catalog. You need excellently observed statistics. You must feed these lines, yeah? You must feed these lines. If your statistic is poor, then you cannot have a good fit for B-value. B-value is just a coefficient of this line. To have coefficient of this line, you need very good catalog. And when you start your injection and you make your stimulation operation, then in the very beginning you have zero catalog, you have no catalog. Then your catalog increases and increases, but this may be already too late. Yeah. So this is why B-value should be taken from tectonic observations and other things, and usually it is quite well given by one. But in Pohang, this was lower than one. Yeah?
Thank you. Thank you.
You're welcome.
So, Serge, what I was trying to do is go down the chat window and let
us go
chat
to
questions talk.
Yeah.
I think we're at Omid. I'm gonna apologize for the name. Omid Kajade. Are you?
Yes, exactly. I'm here. Yeah, Omid is fine. Thank you, Serge. Thank you, Sean. Thank you, Serge, for the great talk. My question was almost kind of related to a question that Ryan had earlier. Like when you were calculating the probability of events bigger than magnitude M, you assume that induced seismicity is a Poisson process, but at the same time, we know that we have observed. It has been observed, aftershock triggering has been observed in the context of fluid-induced seismicity. For example, in Salton Sea in California, which is a geothermal site. Yes. That's just one example on top of my head. Why using the assumption of Poisson process would be a good assumption for calculating that probability, considering that we know aftershock triggering is kind of a byproduct in some cases when it comes to fluid-induced seismicity.
Okay.
Could you just elaborate on that a little bit? Thank you very much.
Okay. Yes, we assume the Poisson process because this is just the simplest assumption. and however, not only simplest assumption, but also more or less corresponding to the observations. So basically, by induced earthquakes, especially big ones, we are interested not in the aftershocks, but in the main events. And main events, they usually have Poissonian statistics. This is the point number one. Point number two, usually we use for our predictions, we use so this is why we're using for computing the worst case probability, we're using the Poissonian statistics because we are interested there in worst case probability of main event and not of the aftershock. Now, on the other hand, as I already told before, for computing the seismogenic index, we neglect aftershocks usually because they are actually not really present there, because we work with events with magnitude 1, 2, or something like this. Yeah, even so, even if you have 3, then you usually don't see, you just do not observe aftershocks because they are to a largest part below the completeness magnitude. So this is why we do not work with aftershocks. But if you have influence of aftershocks, you should try, of course, take them into account. No questions.
Okay, thank you.
Okay, so this was last question.
And Gail Atkins compliments you on the presentation, Serge. And then I think the next question down is Jens. Jens, you want to?
Yes. Yeah, Jens has a question. Yeah, exactly.
Yeah, this is a practical one and very much related to what we were talking about, and specifically Sean's question about evaluating hazard, given that the seismogenic index can increase. So if you take an extreme but maybe not unrealistic example of injecting next to a plate boundary or something, and you want to test what the maximum magnitude might be in that area, the initial injection would provide you with a low seismogenic index, but then you might be led to think that your maximum. So how do you recommend accounting for the possibility that initial short test of low volume might give you a lower estimate than you would get during actual stimulation?
Yeah, this is a good, very good question. So, and this means that you know that you go into tectonically very heterogeneous medium. Then you know this is like an aliasing in signal processing. So in order to correspond to correctly discretize your signal, you must have sufficient sampling. So this means that you must have here also sufficient sampling of the seismogenic index. So that no other way. Yeah.
Yeah, I'm going to throw something out. I mentioned before we started, I was just in a geomechanics course by Professor Zobak. So I'm going to channel my inner Zobak and say maybe 3D seismic would be a solution to that problem, that identify the at least the seismically mapped faults of concern, and then target that for the injection test. So at least you're going directly to the problem. And
you might have an idea, because the 3D seismic will be picking up the biggest faults, most likely. You might have an idea of whether your initial test is reaching faults of the size you might expect to actually fail.
Maybe what one can do maybe such a small experiment, and then use a kind of ideas using this 3D seismic, how you can interpolate or extrapolate this estimates of seismogenic energy, something like this.
Serge, I have a question. So you mentioned about the diffusive behavior in your assumptions for this model. So, but in hydraulic fracturing, it's not usually diffusive fluid flow. It's just convective flow along the hydraulic fracture and partially to natural fractures. So how can we explain this if we consider this convective fluid transport rather than diffusion? And also you consider like some stimulation area, that the stimulation area may not have perturbed pore pressure. So if you mean like poroelastic stress disturbance, maybe that can be explainable, but usually for hydraulic fractures, it doesn't influence large volume of rock for pore pressure. To explain it like in a diffusive mechanism of fluid flow.
Okay. So basically, in the generalized seismogenic index model, you can use any type of physics for using this model. So any type of physics. So just compute this stuff, and from your ideas about your physical process, what are behind, and then substitute here, and then you can go ahead with this. This is for arbitrary physics, including the hydraulic fracturing. What is interesting that this model in this simple form, we also applied to hydraulic fractures, and it works very, very well. So this is hydraulic fracturing in Cotton Valley. This is hydraulic fracturing, this green one in Barnett Shale. We also applied this for Horn River, and everywhere we had an excellent agreement in all case studies what we observed. We have excellent agreement with this equation. So basically, this equation is valid for any type of nonlinear diffusion. So this means that you can have a diffusive behavior as a linear diffusion of the pore pressure, or you can have extremely nonlinear behavior of your medium, so that to produce that by injection, you create permeability by injection. And this permeability and additional porosity are created by your injection, exactly like you do this by hydraulic fracturing. So this is why actually this equation in this form is also quite well for hydraulic fracturing processes. Mm-hmm. Because basically you can look at them also as a very nonlinear diffusion process.
One could argue, with that, because I mean the plots that you show for those two cases, correct me if I'm wrong, these are long-term injection jobs, right? These are the older stimulations where you inject large volumes for a very long time. So they are almost like, in some ways, disposal wells. But how about a rapid hydraulic fracturing job? Has this been tested against that kind of it?
So look again. So this is the Cotton Valley. This is just I think 3 hours or 2 hours. This is also 2 hours or 3 hours injection. So
but I mean those are they were going over 8 hours or almost half a day injections a lot of times.
No, but they're both vertical well stimulations versus multi-stage hydraulic fracturings on a long model for these. Clear.
Okay.
This was standard hydraulic fracturing operations, short ones. But we also applied this stuff. So this very interesting. So we have recently, a couple of years ago, published a paper on application of nonlinear models to hydraulic fracturing observations after you stop your injection. So you make hydraulic fracture and then you stop. What happens with seismicity there? There is the so-called backfront propagation, so I think this is Journal of Geophysical Research 2016 or 17 or something. And Lisa Johan is the first author. Johan, you can look at this, and then there are their observations. Of the behavior of seismicity, propagation of seismicity in space as function of time. And it is excellently described by nonlinear process. So and these are very short. So what means short? Couple of hours hydraulic fractures, and then couple of hours observation of seismicity after the hydraulic fracture. These are also data published. So we just use data published elsewhere.
So Serge, on chat, there's just 2 other messages. Again,
absolutely.
Jingu Lee and Alexandros Savides. So compliment. So I think that covers everything in chat. Is there anybody else? I know there's a number of people still online. Does anybody have any questions? They'd unmute, and as long as Serge is.
I'm here. So I'm glad to have this very interesting discussion. This also very rich questions. They are very interesting for me.
Ahmed, you got your hand up.
Yes, I have just a very quick question about the nucleation time. I think you mentioned, and maybe I just missed it. So the nucleation time was the time from start of the fluid injection?
Exactly, from first operation. So even in the Pohang, this was just the mud loss. Okay.
And can we actually measure this thing from our seismic catalogs?
Absolutely. If you know where you started your operation, and usually you know. So this for Pohang, this was the start.
Okay.
And this was the nucleation time. So up to this was a Pohang earthquake. This is the nucleation time for Pohang.
So Serge, just a question on that. When you say mud loss, that's a mud loss during the drilling of the event?
Yes, this was very interesting. They drilled, so just a second, I will show you the borehole. They drilled this one, and then it seems to be that they intersected the earthquake fault. And there was 600 cubic meter mud loss in this fault.
And from the seismicity plot you had, that drilling mud loss caused a magnitude 1, if I understood correct.
Excuse me, I haven't understood you.
If you go back to your magnitude with
yes.
operational plot.
Just a second. Yeah. There was already induced seismicity, you see here, from the mud loss.
A magnitude 1 event.
Yeah.
From mud loss.
Yes. This was one, and there was also small event, but this was one. Yeah, this was one from mud loss, and then so this, yeah, that's right.
So maybe we don't have to do a small injectivity test. We can just, as we're drilling.
No, but I would say that mud loss is not a good sign. Yes.
I agree, but if you're seeing seismicity with mud loss.
I have another question. So regarding the disposal-induced seismicity combined with hydraulic fracturing seismicity, for example, in West Texas, these earthquakes are recorded originating from both of these. So in the catalog, you have a group of seismic events that are related to both of these. So what you showed in the comparative plot, this hydraulic fracture-induced seismicity may be different for the seismogenic index from the disposal-induced seismicity. So when we record the catalog in West Texas, we may combine these two together and reach to a combined seismogenic index. So how can we clarify this? Because it's like in whatever.
Okay. Just let us. This I assume that you mean this plot. So this was hydraulic fracture. This was hydraulic fracture. This was approximately this event.
Oh, okay.
And this ones. This was maybe this ones. This was disposal ones.
So you mean you can quickly distinguish that by the magnitude of the event?
No. This just I know where data are coming from. Yeah. So, but basically, yes, they are clearly distinguished. One can clearly distinguish them. And also this stuff with Sesmogenic index. What I presented, this is just for direct injection induced things. Yeah. So with fluid disposal, this is a little bit more complex situation. Yeah. Because you have there a little bit different geometry. You have here, say you have this is sediments, and this is your crystalline basement. Yeah. This is the crystalline basement, and basically you put fluid into this arbuckle formation,
yeah.
And basically what you do there, this is something like this. Firstly, you say fill this layer, this reservoir with fluid, and then fluid start to diffuse, the pore pressure start to diffuse down.
Right.
And then it triggers the things here below.
Yeah.
Yeah, this is a little bit complex geometry. Yeah, so we published a paper about this. Also, this was, I think, also Lisa Johan, the same name what I already put it on slide, and this was scientific report, maybe 2016 or 17, I don't remember now. And we proposed a special model. We considered even the events triggering and so on and so on. You could look there if you are interested in the topic. You could look at this publication. I think this is a reasonable model what we propose there. We call even this underground reservoir induced seismicity. Underground reservoir, URIS. This is the URIS model of induced seismicity.
Thank you. I appreciate it.
Yeah, you're welcome. So there is chat, still more chat.
Yeah, I think there's a couple more congratulatory comments.
Yeah, some positive comments. Thank you very much.
Yeah, but really excellent discussion. So, Serge, I think you win the record for the most engaging and longest post presentation discussion we've had. So, thank you.
Thank you very much. Thank you, Sean, for inviting me here. I appreciate a lot this invitation. Thank you.
No, we appreciate
Thank you, Serge.
Yeah.
This is very useful work for a lot of people. Appreciate it.
Thank you. Thank you. Thank you very much.
Thank you, Serge. I appreciate your presentation.
Thank you, guys. So I'm stopping to share my. I must stop.
Yeah, so I will post this recording on our YouTube channel. So for everyone who want to watch it again, it will be available this afternoon.
Will this also include questions?
Yes, all of it.
Excellent.
Yeah.
And so Ahmad's still on the line. Ahmad, this just brainstorm an idea here quickly. We're with the ARMA workshop, the idea of site characterization and these kind of discussion we had here with kind of test injections might be a good discussion topic for Santa Fe.
Yeah. That is trying to do that in the context of predictive models.
Exactly. Yeah. And Serge, it's in Santa Fe, so it.
Okay. Thank you very much.
Be a good one to put on your calendar.
Yeah, I will put it. I will put it. This is in June. Yes.
Yes.
Correct. Yeah.
This in June. Okay. So I will try. We will see what will happen. Yeah, to this time. Yeah, I plan to visit United States just next week. Yeah, I plan. Yeah.
We all understand, but there's benefits to this webinar series is something that
nearly 2.5 years I have not visited the United States. This is terrible for me.
Yeah, the pandemic's been terrible for everyone, but positive outcome has been this webinar series that we initially kicked off as something to help fill the gap with the pandemic. It's continued on post. Well, we're still in the middle of it, but as things open up, so. All right. Well, thanks, Serge. I know it's late there, but
thank you
again, and hope to see you.
Thank you very much.
Thank you.
See you next time.
Thank you, everyone.
Bye.
Thanks, everyone.
Thank you. Okay. Mahdi, could you send me then the link to the? Great. Thank you very much.
Definitely. I will send you the link for the recording.
Yeah. Thank you, guys, for good organization. Excellent.
Thank you so much. I appreciate it. Have a good evening. Thank you. Bye-bye.
Same to you guys. Bye-bye.
Thank you. Bye-bye.